Right now, more than 15 billion miles from Earth, a machine built before the invention of the personal computer is about to attempt the most dangerous operation of its life. It has survived launch, radiation, the killing cold of deep space, a corrupted memory chip, a transmitter that switched itself off, and thruster lines clogged with decades-old fuel residue. Nothing has stopped it. Not yet. But now it's running out of something that can't be fixed, replaced, or repaired from Earth: electricity. And the plan NASA has built to save it has a name that sounds almost too dramatic to be real. They're calling it the Big Bang. Stick around, because by the end of this video you'll understand exactly what that plan does, why it could either extend the spacecraft's life for years or end it in 2 days flat. And that second possibility is closer than you think. Here's the strange part. Nobody will see this operation happen. There's no launch pad, no visible spark, no moment you could point a camera at. And yet the outcome of this one sequence may decide whether we keep hearing from the most distant machine humanity has ever built, or whether its voice simply stops. Let's clear something up immediately, because the name is misleading. This is not a new engine. There's no explosion, no burst of thrust, no dramatic course correction. Voyager 1 is not turning around, and it is not heading back toward Earth. The Big Bang is the nickname engineers gave to a plan for rearranging Voyager 1's remaining electrical systems, all at once, in a single tightly choreographed sequence, instead of one careful step at a time. Certain components would be shut down, lower power backups would take over, heaters and support systems would be rebalanced so the spacecraft doesn't freeze in the process. The entire goal is to squeeze out more electricity without losing control of the ship. That should sound simple. It isn't, because of what NASA is actually working with. Voyager 1 launched in 1977. Its onboard computers have less processing power than a musical greeting card. Every command sent to it has to be built using documentation and procedures preserved for almost 50 years. Many of the engineers running this mission today weren't even alive when it launched. And there is no reset button. None. Here's what makes this genuinely nerve-wracking. NASA can't watch this happen. A command sent to Voyager 1 travels at the speed of light, but the spacecraft is now so far away that light itself takes almost a full day to reach it. Then NASA has to wait for Voyager to receive the command, execute it, generate a report, and beam that report back across the same immense distance. Add it up, and engineers won't know whether the very first command in the sequence worked until nearly 2 days have passed. If something goes wrong with a spacecraft closer to home, Mission Control can react in seconds, send a correction, flip it into safe mode. Try again. With Voyager 1, every decision is separated from its outcome by billions of miles and the better part of 2 days. If temperatures start falling, or voltage drops too far, or onboard software misreads the sequence, there's nothing anyone on Earth can do about it in real time. So how do you test something you can't watch, on a machine you can't touch, where a single mistake might not reveal itself for 2 full days? You don't test it on the one spacecraft you can't afford to lose. That's exactly why NASA didn't want to try this on Voyager 1 first. Instead, the plan was tested on Voyager 2, its twin. Voyager 2 is a little closer to Earth and has slightly more electrical power to spare, making it the closest thing NASA has to a safety net. The two spacecraft were built identically, but they've lived very different lives, different paths through the solar system, different failures over the decades. Still, watching how a 50-year-old Voyager handles this kind of power shuffle gives engineers something they'd otherwise have to guess at. Testing ran through May and June of 2026, with engineers watching for the same handful of signs every time. Did voltage stay inside its expected range? Did the backup components draw the amount of power the models predicted? Did temperatures in the surrounding systems hold steady instead of drifting toward dangerous extremes? Every one of those readings had to be pulled across the same punishing communication delay, hours at a time, before the next step could even be planned. If Voyager 2's results held up, the plan for Voyager 1 could move forward no earlier than July, which is exactly the window we're in right now. That doesn't confirm a successful Voyager 1 operation. It means the mission has entered the phase where final checks and go or no-go decisions matter more than at any point in years. To understand why NASA is willing to gamble at all, you need to understand what's killing this spacecraft, slowly, 1 watt at a time. Voyager 1 doesn't use solar panels. On this far from the sun, sunlight is far too weak to be useful. Instead, it runs on radioisotope thermoelectric generators, devices that convert heat from the natural decay of plutonium-238 into electricity. Plutonium-238 doesn't decay quickly, but it doesn't decay forever either, and there's no way to refuel it, recharge it, or slow it down. That heat has been fading since the day of launch, and it will keep fading no matter what NASA does, no matter how carefully engineers manage the rest of the spacecraft. Current estimates put the loss at roughly 4 watts of usable power every year, a number that never goes back up. 4 watts doesn't sound like much. A single light bulb can use more. But Voyager 1 has already been stripped down to bare essentials. The cameras that photographed Jupiter, Saturn, and the pale blue dot have been dark for decades. Backup systems have been sacrificed one by one. Entire science instruments have been switched off, not because they stopped working, but because there simply wasn't enough electricity left to run them. Think of it like keeping a hospital running on a shrinking power grid. First, you cut the lights in empty rooms. Then you dial back the heating. Then you shut off equipment that's useful but not essential. Eventually, every device still running actually matters. And switching off the next one doesn't just save power. It means losing that capability forever. Voyager 1 reached that stage a long time ago. In April 2026, it reached it again when NASA switched off Voyager 1's Low-Energy Charged Particle Instrument, LECP for short, after almost 49 years of continuous operation. During the planetary tour, LECP studied charged particles around Jupiter and Saturn. Later, it became one of the most valuable instruments on the spacecraft, measuring particles as Voyager 1 crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins. Nobody on the team wanted to turn it off, but an unexpected drop in available power forced their hand. The process took hours, and because of the communication delay, engineers couldn't confirm it had worked correctly until the next signal came back. An instrument that had operated since before most of its own team was born went silent in an afternoon. Voyager 1 now runs on exactly 2 active science instruments, one that measures magnetic fields and one that detects plasma waves. That's it. And they're still returning data from a region of space no other operating spacecraft can reach, which is exactly why NASA is considering something this risky to keep them running. Here's the core problem the Big Bang plan is trying to solve. Voyager 1 has redundant components backups engineers installed in the 1970s, specifically because they knew this spacecraft would eventually travel too far to ever be repaired. Those backups have already saved the mission more than once, but after 50 years, nothing about switching to them is guaranteed. Some have sat inactive for decades. Some may be colder than they were ever designed to operate in. Some may simply behave differently now that the spacecraft's whole electrical and thermal environment has shifted underneath them. So swapping a group of systems over, all in one coordinated sequence, carries real danger. A backup component might draw more startup power than expected. A heater change in one part of the spacecraft could cause temperatures to crash somewhere else. A voltage spike could trip an automatic safety routine, and Voyager's onboard computer could respond by dropping into safe mode on its own, with no input from Earth. That's the worst case, a chain reaction. A response designed to protect a young, healthy 1970s spacecraft could now do the opposite to a fragile 50-year-old one. Back when Voyager 1 launched, those safety routines made sense. If a voltage spiked, the smartest move was to shut things down, protect the hardware, and wait for new instructions. Nobody designing that system in 1977 could have imagined a version of Voyager 1 running on a sliver of its original power, where shutting things down might mean losing a heater it can never turn back on. Which means the Big Bang sequence has to do 2 things at once: save power and stop Voyager 1 from trying to protect itself in exactly the wrong way. Now here's the part that makes this worth the risk. If the Big Bang procedure works, NASA believes there's a real chance LECP could be switched back on. That turns this from a bare survival mission into something genuinely exciting. Instead of just keeping the lights on, engineers might recover enough electricity to bring an entire science instrument back from the dead. There's a small detail that makes this possible. When LECP was shut down, NASA didn't let everything connected to it go cold. A tiny motor tied to the instrument, using barely half a watt, was deliberately kept running. If that motor had been allowed to freeze completely, restarting it later might have been impossible. Lubricants and moving parts don't behave kindly after decades in deep space cold. Half a watt spent today, and to protect the possibility of tomorrow. That's the entire mission in miniature. Every fraction of a watt fought over and rationed on a spacecraft that loses about 4 of them every single year. If this all sounds unprecedented, it isn't, not for this spacecraft. In November 2023, Voyager 1 started transmitting data that made no sense. The signal itself was fine, but the information inside it had turned to noise. NASA traced the problem to a damaged section of memory in the flight data system, the computer responsible for packaging science and engineering data before transmission. There was no way to replace the broken chip, no technician who could pop it out and solder in a new one. So engineers did something almost absurd. They split the affected software into pieces, tucked those pieces into other unused corners of memory, and rewrote the internal references so the program could still run as if nothing had changed. A software repair performed across 15 billion miles on a computer from another era, using tools its original designers never imagined. It worked, and for months, the mission had been sending nothing but gibberish until suddenly it wasn't. Then in 2024, the spacecraft unexpectedly abandoned its main transmitter and switched to a backup so weak it hadn't been used to talk to Earth in decades. For a while, the signal was barely a whisper. The team found a way to reconnect anyway. Then the thrusters started clogging. Voyager 1 needs small thruster firings to keep its antenna pointed at Earth. Without them, its narrow radio beam drifts away, and the connection is lost for good permanently, with no way to point it back. Fuel residue had been building up inside the primary thruster lines for years, gradually restricting how much fuel could actually flow. So in 2025, NASA reactivated a backup set of thrusters considered dead since 2004, thrusters nobody expected to fire again, with their heaters turned off to save power. It worked. Every one of those recoveries teaches the same lesson. This team does not accept impossible as a final answer. But the Big Bang plan is different, and that difference matters. Every previous fix targeted one broken system, corrupted memory, a bad transmitter, blocked fuel lines. The Big Bang plan touches the spacecraft's entire power balance at once. It's not repairing one part. It's rewiring how Voyager 1 shares its dwindling energy across everything still keeping it alive, which means the consequences could be slower to show up and harder to predict. Picture this. NASA sends the sequence, several devices switch over, and the first readings look completely normal, voltage holds steady, data keeps flowing, everyone breathes a little easier. Then, over the following days, a temperature in some distant section of the spacecraft starts drifting down, a fuel line gets colder than expected, an instrument's internal clock starts to drift. None of that shows up in the first report, so engineers have to watch Voyager 1 for an extended stretch afterward. Every temperature reading, every electrical current, every status flag, knowing each new test still takes days to confirm, while the power keeps draining regardless of how carefully they wait. There's a symbolic deadline bearing down on all of this too. In November 2026, Voyager 1 is expected to become the first human-made object to reach a full light day from Earth. At that distance, a radio signal takes 24 hours just to arrive, and another 24 to get an answer back. A single yes or no question, answered in 2 full days. When this mission launched, engineers could talk to their spacecraft across the solar system in minutes. Now Earth and Voyager 1 aren't just far apart. They're operating on 2 completely different timescales, and that gap will only keep growing. It's worth remembering what this spacecraft is actually for right now. Voyager 1 finished its planetary tour of Jupiter and Saturn decades ago. In 2012, it became the first human-made object to cross into interstellar space, not by leaving the sun's gravity, which won't happen for tens of thousands of years, but by crossing the heliopause, the boundary where the outward push of the solar wind gives way to the material between stars. Out there, its 2 surviving instruments are doing something nothing else can. The plasma wave instrument picks up oscillations in the thin charged material that fills interstellar space. The magnetometer tracks the direction and strength of the magnetic field around the spacecraft. Together, they're helping scientists understand how the sun's influence interacts with the wider galaxy, and how ripples from solar activity travel outward long after they leave the sun, sometimes taking months or years to reach the spacecraft. No other operating spacecraft is out there to measure any of it. A future mission built with far more advanced technology would still need decades just to reach the distance Voyager 1 has already covered, and every year it flies represents data nobody else on Earth has any way to collect. That's why 1 extra year of operation is worth this much risk. That's why half a watt is worth fighting for. There won't be a countdown when the moment comes. No live broadcast, no dramatic mission control shot for the cameras. It may show up as nothing more than a quiet update on a NASA webpage. But here's what will actually be happening behind that update. One of the Deep Space Network's giant antennas will aim at the tiny patch of sky where Voyager 1 currently sits. The Big Bang sequence will be encoded into a radio signal and sent outward. It passes the moon in about a second. It crosses Mars's orbit in minutes. It sweeps past Jupiter, Saturn, Uranus, Neptune, retracing an hour's a journey that took the spacecraft itself years to make. Then it keeps going, into the dark, for the better part of a day. When it finally reaches Voyager 1, the spacecraft's onboard computer, a design older than most of its engineering team, will decode the instructions and, if everything checks out, begin executing them. And here's the part that's almost impossible to sit with. Earth won't know. Mission Control will be watching data that's already many hours old. Voyager 1 could complete the entire sequence, successfully or not, while engineers on the ground are still waiting to confirm the command even arrived. Then the spacecraft's response begins its own trip home. Another day passes. Only when that signal reaches the Deep Space Network will anyone on Earth know whether it worked. 2 days of silence for one command. There's a human side to this too. Some engineers on this mission have worked on it for decades. Others inherited it from the people who designed and launched Voyager 1 in the first place, passing down documentation, hard-won lessons from old failures, and an almost personal responsibility for a machine that's become more than metal and wiring to the people who look after it. Voyager 1 also carries the golden record, a gold-plated disc packed with sounds, images, music, and greetings from Earth, included on the off chance the spacecraft is ever found by another civilization, millions or billions of years from now, long after every person involved in building it is gone. Its deeper meaning doesn't depend on that ever happening. It's already a message we chose to send, regardless of whether anyone's listening, a small, deliberate act of hope launched into the dark. The spacecraft itself could drift through space for millions, maybe billions, of years after it goes quiet, but the window during which it can still talk to us is closing. The Big Bang plan can't stop the plutonium inside it from decaying. It can't make Voyager young again. All it can do is use what's left a little more efficiently and buy a bit more time before the silence. That makes this whole operation both hopeful and a little tragic at once. Success doesn't mean Voyager 1 lives forever. It just means we get to hear from it a little longer. So here's where things actually stand. Do nothing. And Voyager 1 keeps losing about 4 watts a year until another instrument, and eventually another critical system, has to be shut down for good. Attempt the Big Bang plan, and there's a real chance to buy back years of operation, and maybe even bring LECP back online. But there's also a real chance the sequence destabilizes a balance this spacecraft has held for decades, with no way to intervene once the command is sent. There is no safe option here. There is only the option that gives Voyager 1 its best shot at continuing. NASA isn't attempting this because Voyager 1 found something extraordinary out there, and it isn't turning around or coming home. It's doing this because the spacecraft is running out of time, and because 49 years of near misses have taught this team that impossible has never been the final word with this mission. When that command finally goes out, somewhere inside the deep space network, an antenna will send a carefully built signal toward a point of light, too faint for any human eye to see. Almost a day later, Voyager 1 will receive it. Relays may shift. Devices may power down. New components may take over, and temperatures and voltages will begin drifting toward whatever comes next. Then it will send its answer, and Earth will wait for nearly 2 full days to find out if humanity's most distant messenger made it through. If it does, the Big Bang plan buys Voyager 1 more time, and maybe a silent instrument speaks again. If it doesn't, the recovery attempt begins all over, one command at a time, across a gap that's about to reach a full light day wide. Either way, one thing is already true. The spacecraft has outlived every deadline anyone ever set for it. Betting against Voyager 1 has never once paid off. Think about what that actually means. A machine designed for a 4-year mission to Jupiter and Saturn is still working, still thinking, still listening for instructions from a planet its builders knew it would never see again, nearly 50 years and 15 billion miles later. Every watt it has left has been fought for by people who refuse to let it go quietly. That's not an accident of engineering. That's a choice, made again and again for half a century. The answer may already be on its way through the dark. Somewhere on Earth right now, a small team is refreshing a screen, waiting on numbers that are already hours old by the time they appear, hoping the next line confirms that Voyager 1 is still out there, still listening, still willing to answer. If you want to know what happens the moment that data comes back, subscribe, because when Voyager 1 responds, this channel will be one of the first to tell you.